Einstein's theory of gravitation. We have already discussed the equivalence principle and principle of covariance in one of our earlier lectures. The equivalence principle is about the equivalence of a uniformly accelerating frame and a frame of reference under the influence of gravity. It says that it is impossible by means of local experiments in space-time to distinguish between the effect of gravity and that due to a uniformly accelerating frame of reference. So that means by no local experiments in space-time, experiments involving any law of physics and any interaction, can one distinguish between gravity and the effect due to a uniformly accelerating frame of reference. And by the way, this equivalence is only local. So if we perform an experiment which is not local, so for example, by moving to some other point in space-time, we will be able to distinguish between the influence of gravity and that due to a uniformly accelerating frame of reference. So only by means of local experiments can this equivalence be, only locally can we establish this equivalence. So that means there is no gravitationally neutral object with respect to which we can measure gravity, and therefore there will be no consistent way of defining acceleration due to gravity. So which means that we should abandon the idea of gravity as a force that produces acceleration. And not only that, all material particles, irrespective of their mass, will follow the same trajectory provided they start from the same initial conditions. So that means the trajectories of particles, material particles that experiences only gravity falls under a particular class of trajectories, and they are universal because their trajectories are independent of the mass of the particle, and such a universal class of trajectories are called unaccelerated or freely falling trajectories. And they are called unaccelerated because we no longer consider gravity as a force producing field, and therefore there is no so these objects, so these trajectories are considered as trajectories of non-accelerated particles, and they are universal, so they are independent of the mass of the material particle that is moving, and therefore they need to be associated with some property of the space itself. Further, since these freely falling trajectories are universal, even though we need to abandon the concept of the concept of gravity as a force producing field, we can have this set of a universal class of freely falling trajectories, and we can construct coordinate systems attached to such trajectories. So we can start with a point on one of those freely falling trajectories at a particular point, and then construct inertial coordinate system as we have done in the case of special theory of relativity, by having three mutually perpendicular Cartesian axes measuring the Cartesian coordinates, and having synchronized clocks placed at every Cartesian grid point thus constructed. Now, the equivalence of a frame of reference under gravity with a uniformly accelerated frame is only local, and therefore if this local frame is seen from another point in space-time, a point which is different from the one at which we have constructed this inertial frame, it will look like an accelerated frame. And therefore we see that we can construct these local inertial frames at every point along the trajectory, but these local inertial frames of reference are unaccelerated only to the particular point at which they are constructed. So we can consider the space-time as a curved space which allows for the construction of local inertial coordinate systems. And the mathematical structure that is consistent with such a requirement is that of a differentiable manifolds, which will allow a curved space in which local coordinate systems can be defined. So to construct the relativistic theory of gravity, one has to consider the space-time as a curved manifold and then construct or obtain generalizations of the laws of physics in the curved space-time. Now, the principle of covariance implies that the laws of physics should be the same for, or should have the same form for all observers. Now, in a curved space, the equations representing the physics laws, the laws of physics, will have the same form to different observers, provided they have the same form in the coordinate systems that they are using. An equation that is represented as a tensor equation will have the same form in any coordinate system, and therefore the principle of covariance would then imply that the laws of physics should be expressed as tensor equations. Secondly, in space-time, since it is a differentiable manifold, one can construct local inertial coordinates in which the Christoffel symbols can be taken to be 0, and such coordinates are called geodesic coordinates. And finally, the Einstein equivalence principle says that the laws of physics should reduce to those of special theory of relativity in small enough regions of space-time. So this would imply that the metric tensor for the curved system, which is given by, say, G mu nu, should reduce to that of the Minkowski space-time, the space-time of special relativity, and the metric tensor given by eta in geodesic coordinates, because in geodesic coordinates correspond to the local inertial coordinate system, and in geodesic coordinates we would expect the metric tensor of the space-time to reduce to that of the Minkowski space-time. Then we can use a principle called the minimal coupling principle in generalizing the laws of physics that is valid in flat space-time. So take a law of physics that is valid in inertial coordinates in the flat space-time. So that is a law of physics that is valid in special theory of relativity. Then write it in the form of a tensor equation for the curved space-time and assert that this is the valid generalization of the corresponding physical law for the curved space-time. So the first step involves writing a law of physics which will be represented by an equation in inertial coordinates in a flat space-time. So that will be an equation valid, a tensor equation valid in the flat space-time. Then we need to generalize it to a tensor equation for a curved space-time, a general space, curved space, and then we assert that this new equation represents the law of physics in the curved space-time. Whether this actually corresponds to the physical law or not should be verified by experiments. We now consider the generalization of Newtonian gravity to the case of relativity, to the case of curved space-time. The Newtonian relativity involves two equations. First of all, the response of a material particle to a gravitational field, and secondly, how gravitational field is produced or affected by the presence of matter in space. The first case is given by Newton's second law of motion. Suppose we have a material particle, then Newton's second law says that the acceleration of the particle, which is dv by dt, where v is the mass of the particle, is given by the force per unit mass acting on that particle. But the force per unit mass is given in terms of the gravitational potential as negative gradient of the gravitational potential at the particular position of the particle. So the particle is at r and it has a velocity v, and dv by dt equals minus gradient of phi at r. Now, what is the origin of the gravitational field? In Newtonian gravity, a gravitational field is produced by a mass distribution. So a single particle of mass m, say at a particular point, and taking its position as the origin of coordinate, it produces a gravity field around it, and the potential field at a particular point of coordinate position vector r is given by phi of r, and according to Newton's law of gravitation, this is given by g m by r, where r is the magnitude of this position vector. So r is equal to magnitude of minus gm by r. However, if we have a distribution of material particles instead of a single particle, then we need to consider, we need to subdivide this distribution into infinitesimally small regions, and if this distribution is described by a density rho, and if the position of this infinitesimally small element is given by the position vector r dash over here, then the mass of this infinitesimally small element would be given by rho r dash, which is the density, times the volume of that element, which we write as dr dash, which is the infinitesimally small volume element. So this m corresponding to this infinitesimally small element over here at a distance at a position vector r dash with respect to this origin of coordinates is given by rho r dash times dr dash. Then the potential due to this element is given by minus g times rho r dash dr dash divided by the distance of that particular point from this position. If the position vector of this point is given by vector r, then this and this by r dash, then this vector is given by r minus r dash. And instead of this factor, we will have r minus r dash in the denominator. So this is the potential field at this particular point, let us call it P, due to this infinitesimally small region of mass distribution. Now the total potential field at this point is computed using the superposition principle, which would say that the total potential field at this particular point is simply the sum of the potential due to all such infinitesimally small elements constituting this mass distribution. So if we take this sum, and since we are taking infinitesimally small elements, this will be replaced by the integral, and the total potential at phi at r is given by the integral of this whole thing over all volume. So we have the potential due to a mass distribution given by minus g integral dr dash rho r dash, then absolute the magnitude of r minus r dash. To get the differential form of the Newton law of gravitation, we take the Laplacian of this potential. So del square phi of r, where this derivative is taken with respect to r. We have to do the same on the right hand side also. Now the only term with r dependency is this one. So I can take this del square inside the integral, and dr dash rho r dash can be taken to the left. Then the Laplacian acts on this factor only. And we already know that Laplacian of 1 by r minus r dash is simply minus 4 pi times the Dirac delta of r minus r dash. So we will get del square phi r equal to 4 pi g integral dr dash rho r dash delta of r minus r dash. The integration over the Dirac delta is quite simple. We just have to replace the factors of r dash by r, and we will end up with the result del square phi of r is equal to 4 pi g times rho of r. Now we need to generalize this theory of Newtonian gravity to be applicable in curved spacetime. So we have two equations. The first one is this equation, which correspond to the response of material particles to the presence of gravitational potential or gravitational field. And the second one is how gravitational field is affected by the presence of matter. So matter produces gravitational field, and matter in turn gets affected by gravitational field. First, we consider the effect of gravitational field on matter and generalize the Newton's second law in the case of curved spacetime. So we again appeal to the minimal coupling principle, and we find the corresponding equation in the case of flat spacetime in inertial coordinates. So this corresponds to the law. So this corresponds to the force equation in special theory of relativity. We should first understand that if a material particle is affected only by gravity, we will no longer consider it as an acceleration producing field. So the acceleration producing force, and therefore the force over here in the curved spacetime in the presence only of gravity is taken to be zero. Further, in special theory of relativity, the force equation is generalized to the following form: dp mu by ds is equal to 0, where p mu is the force momentum, which is defined the following way. First of all, we define the force velocity, which is the tangent velocity on the Minkowski spacetime, so which is defined as dx mu by ds, where ds is the infinitesimal interval on the Minkowski spacetime, which is given by ds square is equal to eta mu nu dx mu dx nu. Then if m represents mass of the material particle in a frame of reference in which it is at rest, then we can define p mu as m times u mu, which is equal to m times dx mu by ds. Now, in special theory of relativity, the force equation, the generalized force equation is dp mu by ds equal to g mu. But if the material particle experiences no force, this will become dp mu by ds equal to 0. So according to the minimal coupling principle, we should generalize this equation to be valid in a curved spacetime. So this can be done in the following two steps. First of all, we need to define what p mu is. we can generalize these equations to the case of curved spacetime. So the interval ds square will become ds square equal to g mu nu dx mu dx nu, where g mu nu correspond to the metric tensor of the curved spacetime. Then we can define the four velocity, the tangent vectors on the curved spacetime as u mu as dx mu by ds, and the four momentum simply as p mu equal to m into u mu equal to m into dx mu by ds. Now the only thing that has changed is this ds, which is now given by this equation. Further, m here is the mass of the particle measured in a frame of reference in which it is at rest. So if you replace this p mu by this p mu defined in the case of a curved spacetime, this will still be dp mu by ds equal to 0 in the absence of a force. Now remember, because of the equivalence principle, we can no longer consider gravity as a force producing field, and therefore we have abandoned that idea of it producing an acceleration, and we will consider particles moving under gravity to be non-accelerated, and therefore we will not consider gravity as a force anymore. And in that case, when we generalize this equation to the case of the four-dimensional space-time with gravity, there is gravity alone, we will take the force g mu to be equal to 0. So the generalization of this equation, so the generalization of dp mu by ds is equal to g mu to the case of the curved spacetime would be dp mu by ds is equal to 0, because gravity is no longer taken to be a force here in the new case, in the curved spacetime. But then we need to consider the second principle, the principle of covariance, which would require the equations representing the laws of physics to be tensor equations. Now, even though this is a contravariant vector p mu, dp mu by ds is no longer a tensor. So in a curved spacetime, in flat spacetime this would be a tensor, but in curved spacetime this will not be. The corresponding tensorial derivative is the intrinsic derivative. So we need to replace this with the intrinsic derivative of p mu with respect to s. So the generalization of dp mu by ds is equal to g mu, or equal to 0 in the case of flat space-time, to the case of the curved space-time. Here the force could be gravity force in special theory of relativity, but in general theory of relativity, in curved space-time, the gravity will be taken to be will not be considered as a force, and therefore the force term has to be taken to be 0, and the left hand side has to be taken as a tensor. So we generalize this to dp mu by d tau to be, sorry, dp mu by ds to be equal to 0, where dp mu by ds over here is the intrinsic derivative. And as we have already seen, the intrinsic derivative, so dp mu by ds is equal to 0, but p mu is equal to m times u mu, so this is equal to m u mu by ds is equal to 0, but m is the mass measured in the rest frame of the particle, so it's an invariant quantity, so it can be taken outside over here, and then we can cancel this factor of m. So we will end up with du mu by ds equal to 0, and that's the equation I have written here. Now the intrinsic derivative of a quantity is defined in the following way. du mu by ds is equal to the ordinary derivative plus gamma mu alpha beta, then u alpha, this is mu, then dx beta by ds. But dx beta by ds is nothing but u beta. So this equation now becomes, by the way, and u mu is equal to dx mu by ds, and therefore this first term becomes d square x mu by dx square. So that is this equation. Then the second term is gamma mu alpha beta. Then this quantity is dx alpha by ds, and this quantity is dx beta by ds. So I have dx alpha by ds and dx beta equal to ds. Dx beta by ds, and the right hand side is equal to 0. And this is nothing but the geodesic equation. So the trajectories or the world lines given by this equation are geodesics in the curved spacetime. So now we see that the material particles that are falling only under gravity, which are called the free falling particles, their world lines will be represented by this equation, which is the geodesic equation for the spacetime. So that's why we have the first result that the world lines of free falling particles are geodesics in spacetime. So we have arrived at the generalization of the response of material particles to the gravity field. In fact, gravity is no longer considered as a force producing, as an acceleration producing force. Rather, it is a property of the space-time, and in fact, their trajectories are special and they are given by the geodesics of the space-time. So we have got the generalized equation, and the next thing is to check whether this is a correct equation or not. And the first verification for this is that this equation should reduce to the equation given by Newton's second law in a proper limit. So this will correspond to a limit in which gravity is extremely small, and we call this limit the Newtonian limit. So the Newtonian limit is defined in the following way. First of all, we assume that the velocities of the particles involved are extremely small compared to the velocity of light, or in other words, Vi is much less than c, where Vi are simply the derivative of the coordinates with respect to t, and these are the spatial coordinates. I can take only values 1, 2 and 3. And then we see that dxi by d tau, where tau is the proper time interval, which is related to the interval, space-time interval, in the following way. ds square is equal to c square d tau square. So now dxi by d tau, where I runs from 1 to 3, is given by dt by d tau times dxi by dt, where dt is the time interval measured in its frame of reference, and d tau is the proper time of reference, as a proper time interval. Now dxi by dt is equal to Vi, and this Vi is extremely small compared to the speed of light, and therefore if I replace this by c, this quantity will be much less than that result. So dt by d tau times dxi by dt is much less than dt by d tau times c, because dxi by dt is much less than c. Now this can be written as dct by d tau, because c is a constant. But Ct is nothing but x4. So we have the result dxi by d tau is much less than dx4 by d tau. So this is the first condition for the Newtonian limit, that is the velocity of the particles are much smaller than the velocity of light, which leads to the following result where dxi by dt is much less than dx4 by d tau. And the second condition is that the gravitational field is so weak that the curvature of the spacetime is or very small, and the metric tensor is very close to the metric tensor of the Minkowski spacetime. So G mu nu is very close to the metric tensor of the Minkowski space, and therefore it will be written as eta mu nu, the metric tensor corresponding to the Minkowski space, plus a small modification which we will write as h mu nu, where the magnitude of h mu nu is much less than 1. And the third assumption is that the gravity field is static, that is, it will not change much with time. So we expect then the metric tensor to be independent of time. So that means if we take the derivative of the metric tensor with respect to x4, which is g mu nu comma 4, so this would be the derivative with respect to x4. x4 is nothing but ct, and therefore this will be 1 by c times derivative of g mu nu with respect to t, and that should be equal to 0, because derivative of metric tensor with respect to time is taken to be 0. So the Newtonian limit involves three things. The first one is that the velocity of the material particles involved are extremely small, and therefore dxi by d tau are all much smaller than dx4 by d tau. And the second one is the gravitational field is very weak, and therefore the metric tensor g mu nu can be written as that of the Minkowski spacetime, which is eta mu nu plus h mu nu, where the perturbation h mu nu are extremely small. It's the absolute value of each component is going to be much smaller than 1. And the third one is that the field is static, that is, derivative with respect to time of the components of metric tensor is 0. Now we consider the Newtonian limit of the generalized equation that we just got, that is the geodesic equation of the curved spacetime. So the geodesic equation is given by d square x mu by ds square plus gamma mu alpha beta dx alpha by ds times dx beta by ds is equal to 0. Now replacing ds as c d tau, we have a factor of 1 by c square here and d tau square here, and there is a factor of 1 by c square here, d tau here, and d tau here, and the factor of 1 by c square can be cancelled. So we will end up with this equation: d square x mu by d tau square plus gamma mu alpha beta dx alpha by d tau times dx beta by d tau equal to 0. Now we note that dxi by d tau is much less than dx4 by d tau for all values of I. Further, this term, the second term, involves a summation over alpha and beta. So when alpha equal to 4 and beta equal to 4, this term involves dx4 by d tau times dx4 by d tau. So dx4 by d tau square. For all other cases, one of alpha or beta will be 1, 2 or 3. So we need to compare this term which correspond to alpha equal to beta equal to 4 with terms which are of the following type. So dx sum alpha by d tau times dxi by d tau. Alpha could be 1, 2, 3 or 4 and I could be only 1, 2 or 3. But now we see that even if this alpha is equal to 4 and we need to compare these two terms, but then we see that we have a factor of dx4 by d tau here times dx4 by d tau, and on the second case or second term we have dx4 by d tau and dxi by d tau. So even if we take these two out, we need to compare dx4 by d tau with dxi by d tau, and we already know that dxi by d tau in the Newtonian limit is much less than dx4 by d tau. So terms of this type are negligible compared to the terms of this type. So in the Newtonian limit, we only need to consider this term from the sum involving alpha and beta over here. So retaining only the most important contribution, we will see that this equation simply becomes d square x mu by d tau square plus gamma mu. Then we consider only alpha equal to 4 and beta equal to 4 term. So that is gamma mu for 4 dx4 by d tau square is equal to 0. And now we need to find gamma mu for 4. Gamma mu for 4 is given by g mu nu, then 4 comma nu, the Christoffel symbols of first kind, which can be written as half, then g 4 nu comma 4 plus g 4 nu comma 4 minus g 4 comma nu. Now, in the Newtonian limit, the derivative of the metric tensor with respect to x4 is 0 because the field is static, and therefore this would be 0 and this would be 0, and the only non-zero term comes from this one. So we will have gamma mu for 4 is equal to minus half g mu nu g 4 comma nu coming from this term. And to evaluate this, we need to find g mu nu. We have already seen that the gravity field is so weak that we can write g mu nu, the covariant metric tensor given by eta mu nu plus h mu nu. Now, the contravariant metric tensor with components given by g mu nu follow the following equation: g mu alpha g alpha nu is equal to delta mu nu. So which is the inverse of this matrix if we consider the g mu nu to be a matrix. To find that, we will first write g mu nu equal to eta mu nu minus h mu nu. We could also have written as plus h mu nu, but that doesn't matter. The sign will be taken care of by substituting this in this equation and solving for it. So the contravariant metric tensor is given by this equation: g mu alpha g alpha beta equal to delta mu beta. But then g mu alpha, this one is given by eta mu alpha minus h mu alpha times eta alpha beta plus h alpha beta, which is g alpha beta equal to delta mu beta. Now multiplying eta mu alpha and eta alpha beta, that is this first term, minus this h mu alpha times eta alpha beta plus eta mu alpha h alpha beta, and the next term is h mu alpha and h alpha beta. Now we have already seen that this is h is a very small quantity, and h times h, and that is going to be of the order of h square, and we only want to retain the smallest order terms in h. So since this is of order 2 in h, we neglect that here. So up to first order in h, we only need to consider the first three terms, and we can neglect this term. So we have these three terms on the left hand side, and on the right hand side we have delta mu beta. Now the first term is eta mu alpha, eta alpha beta. But this contraction gives, this inner product gives delta mu beta. Then this delta mu beta cancels with this, and we only have two terms on the left hand side, and right hand side we have 0, and this can be taken to the right side. So we will get h mu alpha eta alpha beta equal to this, that is eta mu alpha h alpha beta. Now if I take inner product with eta nu beta, over here we have to do the same on the right hand side also. So h mu alpha eta alpha beta, then eta nu beta. So on the right hand side I have this eta mu alpha, then this factor which is eta nu beta, then this, that is h alpha beta. But on the left hand side, this is the inner product of a covariant metric tensor with a contravariant one. So the result is the Kronecker delta. The free index over here is nu, and the free index here is alpha. So delta nu alpha. Now the left hand side is h mu alpha delta nu alpha, and the summation over alpha gives h mu nu. So h mu nu equal to eta mu alpha eta nu beta, then h alpha beta. This almost looks like we have raised the indices of h alpha beta with the metric tensor eta here, both the indices, and therefore two factors of the metric tensor. Up to first order, that's correct, up to first order in h. So I have got an expression for h mu nu also in terms of this h, and then I can go back to this equation gamma mu 4 which is minus half g mu nu, then g 4 nu, and substituting that over here we will have minus half, and instead of g mu nu I can write eta mu nu minus h mu nu times, then we have this factor, that is g 4 comma nu. So derivative of g 4 with x nu, but g 4 is equal to eta 4 plus h 4, but eta 4 is simply 1 plus h4. Now I need to take the derivative of g 4 with nu. So this is a constant factor. So I simply wrote eta nu comma eta 4 comma nu here. Eta 4 is 1. Derivative of that factor 1 with respect to nu, x nu is 0. So this factor is 0 plus h 4 comma nu. And that's what we have over here. Now this is already a factor which is of the order of h. Now this is a factor of the order of 1, and this is a factor of order h, and this is 0. So if I expand this, the first term would be eta mu nu times h 4 nu, and that's what I have written here. Now the second term would be h mu nu times h 4 nu. There is a factor of h here and another factor of h here. So this term is of the order of h square. So retaining terms only up to first order in h, I can neglect this term. So the only remaining term is this factor of minus half, then eta mu nu times h 4 nu, because this is 0, because eta 4 is 1. So gamma mu for 4 is minus half eta mu nu h for 4 nu. Then we go back to our geodesic equation, which was like d square x mu by d tau square plus gamma mu for 4 dx4 by d tau square is equal to 0. And we arrived at this in the Newtonian limit because all dxi by d tau were much smaller than dx4 by d tau in this limit. Now gamma for 4 is given by this expression. So substituting for that over here, we have the first term is d square x mu by d tau square. Then for gamma mu for 4, I have minus half eta mu nu h for 4 comma nu times dx4 by d tau square is equal to 0. Okay, so now I need to write this equation and compare it with the Newton's second law, which is written in terms of derivative with respect to time measured in that particular coordinate system, that particular frame of reference, and not in the rest frame of the particle, not in proper time. So we need to find a relationship between the proper time and the time interval measured in any particular frame of reference. So to do that, we first consider the mu equal to 4 case of this equation. So we set mu equal to 4 here, we get d square x4 by d tau square minus eta, then mu is 4 and therefore we have 4 nu, then h for 4 nu times dx4 by d tau square is equal to 0. Now we know eta is a diagonal matrix, and it is given by diagonal minus 1, minus 1, minus 1, 1. Both the covariant and contravariant components are given by the same matrix, and both eta mu nu and eta mu nu correspond to this matrix. And eta for 4 is given by 1. And eta for I is equal to 0. So in this summation involving nu, I will have 4, 1, 4, 2, 4, 3, all of which are 0, and the corresponding terms will be 0. Only when nu equal to 4 is this quantity non-zero. So I can replace this by eta for 4, then h for 4, comma 4, then dx4 by d tau square. Because all other terms with nu not equal to 4 will be 0, because eta for I is 0. Now eta for 4 is 1, and therefore we will have this equal to h for 4 comma 4 times dx4 by d tau square. So equation becomes d square x4 by d tau square minus half h for 4 comma 4 times dx4 by d tau square is equal to 0. Further, we also know that g for 4 comma 4 is equal to 0, but g for 4 is equal to eta for 4 comma 4 plus h for 4 comma 4, because g for 4 equal to eta for 4 plus h for 4. Eta for 4 is already 0, and g for 4 equal to 0 means this also is 0. So this quantity over here is 0 in the Newtonian limit. So this leads to d square x4 by d tau square is equal to 0. Now x4 is nothing but ct. So this is equal to c times d square t by d tau square is equal to 0, and cancelling c, this implies d square t by d tau square is equal to 0. So that means dt by d tau, integrating it once, is a constant independent of tau. Okay, so Then this geodesic equation, which we have written here, can now be written as d by d tau can be written as dt by d tau times d by dt, where dt by d tau is now a constant quantity independent of tau. So doing that, this equation becomes dt by d tau square times d square x mu by dt square, and similarly over here there will be a factor of dt by d tau square times d square x4 by dt square. So our equation is d square x mu by d tau square is equal to dt by d tau the whole square times d square x mu by dt square, and dx4 by d tau square is dt by d tau square times dx4 by dt square. Now dx4 by dt is equal to c, and that's because x4 is equal to ct. So this is equal to c square dt by d tau square. So the geodesic equation becomes, this factor is there, so dt by d tau square times d square x mu by dt square minus half, and the factor is eta mu nu. Yeah. So minus half eta mu nu, then h44 comma nu eta mu nu h44 comma nu times dx4 by d tau square, which can now be written as c square times dt by d tau square because of this, and that should be equal to 0. Now dt by d tau is a non-zero constant, and therefore this can be cancelled, and we end up with the result d square x mu by dt square from this term and minus half c square eta mu nu h44 nu from this term. So the result is this. So now we consider mu equal to 1, 2 and 3. We have already considered mu equal to 4 case. So we have d square xi by dt square. So d square xi by dt square minus half c square eta mu is equal to I, where I runs from 1 to 3, then nu h44 nu. But we already know that this Minkowski metric eta is diagonal. So only when nu is equal to I is this non-zero. So I can replace in the sum, only term that survives is nu equal to I term. So this will be eta I h44 I. And we already know that eta mu nu is equal to this diagonal matrix. So for I equal to 1, 2 and 3, eta II is minus 1, and therefore I can replace this with minus 1. So we will get equation d square xi by dt square plus half c square h44 comma I is equal to 0 for I equal to 1, 2 and 3. Or in other words, d square xi by dt square equal to minus c square. Then h44I is nothing but h d by dxi of h44. There is a factor of half here, so 1 by half and minus here. The left hand side is d square xi by dt square, which is nothing but the ith component of the acceleration in the frame of reference under consideration. So This equation can be written as AI, which is equal to d square xi by dt square, or this can also be written as dvi by dt, where vi is the ith component of the velocity in that particular frame of reference, and this is equal to minus half c square d by dxi of h44. Or we can write this as minus d by dxi of half c square h4. And this needs to be compared with the Newton's equation, the Newton's second law, which says that dv by dt is equal to negative gradient of the potential field, and taking the ith component, I have dvi by dt equal to minus d by dxi of phi. And the comparison of this equation with this equation would give phi as half c square h44. So in the Newtonian limit, the geodesic equation of the curved space-time will reduce to the Newton's equation representing the motion of a particle under gravity, provided we take half c square h44 to be equal to the gravitational potential. Okay. Now, if h44, so if phi is equal to half c square h44, that means that h44 is equal to 2 by c square times phi, and the metric tensor, its component 44, g44 equal to eta 44 plus h44. So that means g44 should be equal to, this is 1 plus h44 is equal to 2 phi by c square. So we have verified that the geodesic equation in the appropriate Newtonian limit reduces to the Newton's equation under gravity, with the choice that the metric tensor g44 is equal to 1 plus 2 by c square times phi.